The physical infrastructure supporting modern AI operates at a scale that strains the global power grid. Data centers housing tens of thousands of GPUs generate massive thermal loads, requiring continuous, high-velocity cooling systems to prevent hardware failure. This chart compares the total power capacity of global AI data centers against national energy grids. Global AI infrastructure now demands 29.6 gigawatts of power, a figure that exceeds the annual power consumption of the entire country of Switzerland. At the individual model level, the environmental cost is severe. Training a single frontier model like xAI's Grok 4 produces 72,000 tons of carbon dioxide equivalent, matching the annual footprint of 17,000 combustion engine cars. This absolute scarcity of power and physical rack space has triggered a direct economic shock across cloud computing. Because available power capacity through 2026 is entirely booked, cloud rental costs for hardware like NVIDIA's Blackwell architecture have surged by 48% in just 2 months, reaching $4.08 per hour. Data centers are throttling under the load, resulting in severe service degradation. Anthropic's Claude Opus 4.6 API recently dropped to a 98.95% uptime, causing enterprise clients like Retool to migrate to alternative providers to maintain business continuity. Adding more compute has hit a hard physical and economic wall. Engineering progress now requires a shift away from brute force parameter scaling. In March 2026, OpenAI permanently shut down its highly publicized video generation model, Sora. While the model achieved its technical performance goals, it collapsed under the weight of its own unit economics. This chart illustrates Sora's financial ledger at the time of its cancellation. The model required a daily inference cost of $15 million in compute just to process user requests, while application purchases generated only $2.1 million in total lifetime revenue. Facing an unsustainable burn rate, CEO Sam Altman moved to triage resources, killing the generative video project to reclaim the GPU clusters Sora was occupying. All of that salvaged processing power was immediately redirected into a single high-stakes foundational model, internally codenamed SPUD. Sora's termination demonstrates that unconstrained generation has detached from commercial reality. To survive, the next generation of models must drastically reduce the amount of compute consumed per output. With parameter bloat no longer viable, the industry is organizing around a new governing metric proposed by researchers at Tsinghua University, the density law. This graph plots the mathematical reality of the density law. Parameters required for a specific intelligence threshold are halving every 3.5 months. As parameters shrink, capability accelerates. AI performance on complex coding tasks is doubling every 88.6 days. Meta is implementing this high-density philosophy by deploying a $14 billion model, Muse Spark, directly into edge hardware like smart glasses. To achieve this, Muse Spark abandons traditional linear computing, where models think in one single thread, and instead instantiates multiple distinct subagents that process different facets of a query in parallel. This is driven by a novel reinforcement learning technique called thought compression. This maps a reasoning chain. The algorithm penalizes meandering pathways, forcing the model to find the shortest mathematical vector. The efficiency gains are immediate. Muse Spark consumes only 58 million output tokens, whereas GPT 5.4 requires 120 million. Artificial intelligence is no longer advancing by thinking longer. It is advancing by algorithmically punishing inefficiency. This push for density extends beneath the finished model, all the way down to the foundational math of pre-training, led by the ByteDance and Tsinghua Nexus Optimizer. This 3D topography models traditional AtomW optimizers. Fed varied data, it settles into a wide, shallow compromise valley. Nexus fixes this by enforcing gradient similarity, dragging the path toward a deep, geometrically shared intersection where distinct data types mathematically agree. Without adding a single parameter to the model footprint, this geometric alignment yields an instant 15% spike in mathematical accuracy on the GSM-8K benchmark. But abstract math can only push so far before hitting physical limits. Memory bandwidth inside the silicon remains the final bottleneck. To compress data further, Huawei engineered the high-float 4 format for their Ascend neural processing units, breaking the traditional 8-bit memory barrier. This schematic breaks down the high 4 architecture. Its three-level hierarchical scaling system tightly packs 64 4-bit elements. This format crushes average storage costs to 4.5 bits per element, maintaining a relative error rate under 1% against full 32-bit precision. Breaking the compute wall demands a synchronized assault. True density is achieved by simultaneously rewriting both the abstract algorithms and the literal data pathways etched into silicon. The cost of compute and the success of density optimizations have fractured the industry architecture. OpenAI is cornering the premium enterprise market with SPUD, focusing purely on logic with a 2 million token context window and persistent cross-session memory. At $100 a month, SPUD provides deep enterprise reasoning, while ultra-cheap, highly dense frameworks like Minimax M2.7 saturate the edge market, running automation tasks locally at a fraction of the cost. But the most severe divergence is in security, revealed when a configuration error leaked Anthropic's classified Mythos model. This radar chart compares Mythos against its predecessor. Mythos achieved a 93.9% score on the SWE bench test. In internal trials, it autonomously discovered 181 zero-day exploits in complex environments and immediately generated the attack payloads. Anthropic has since placed the model under Project Glasswing, locking access behind a strict whitelist granted exclusively to defense agencies and infrastructure partners. Frontier models have speciated into hyper-specialized enterprise processors and strictly controlled digital munitions. As these systems become critical infrastructure and weapons, nation-states are rejecting reliance on centralized foreign server farms. Europe is executing a defensive data sovereignty strategy. Mistral AI has integrated with Accenture to provide large-scale deployments that comply strictly with the GDPR and the new EU AI Act. Simultaneously, the German government is backing merger talks between Canada's Cohere and local developer Aleph Alpha to forge a regulated AI shield for public administration and defense. Japan is executing a radical counter-strategy, leveraging its manufacturing legacy to dominate physical AI. Backed by $6.3 billion in government support, the Japan AI Foundation Model Development Consortium has united SoftBank's architecture with Honda and Sony's industrial hardware. This alliance is injecting trillion-parameter foundational intelligence directly into humanoid robotics, automotive fleets, and semiconductor manufacturing. The compute wall has fractured the industry. Future intelligence will reside in specialized miles, secured behind sovereign data walls, and deeply integrated directly into our physical infrastructure.